So, hello everyone. I am Sudhanshu Kumar from IIT Indore, and I hope you are all doing well. Okay, and so we will continue our legacy of organic named reaction series. Okay, and as you all already know that I have completed 30 name reactions on my YouTube channel. Okay, so you can go and check in the playlist section of organic name reaction. And now we talk about a new name reaction that is called Corey-Chaykovsky reaction. Corey-Chaykovsky reaction. Okay, so first of all, don't be panic after hearing this long name like Corey-Chaykovsky reaction. This is just a name. Uh, th- uh, those scientists uh, which uh, which have discovered this reaction. Okay, so so that's all about this reaction, and we will discuss the whole mechanism a step by step of this reaction. Okay, it means like why this step happen, why not this happen, if this happen, then what will be occur, like so all the possibility I will explain you. Okay, so now let's focus start the reaction mechanism of this name reaction, Corey-Chaykovsky reaction. So suppose I have a substrate like cyclohexanone here, cyclohexanone, right? And and we have taken a reagent like CH3, okay, CH3, and here sulfur is attached. So here is the Ame also, and here is the Ame also, right? So this is the Ame, and here is a positive charge, of course. And we have also taken here base also, base sodium hydride NaH. So as you all know that, so here the product, what will be happen? So here product, what will be formed? So so to predict the product, we have to see the reagent, what is the work of the reagent, then we proceed the mechanism, right? So let me start from the reagent. So what is the reagent? So reagent here is a one is the base and one is a sulfur alide. Okay, yeah, we can make this is basically sulfur compound. So I will explain you in very much detail. Okay, just wait. So as you all know that this NaH is a base, right? This is a sodium hydride, and as you all know that the base work is to take a proton, to abstract a acidic proton, right? As you all know this. Okay, so this is a sodium hydride, this is the base, and we all know that the base takes a proton, the base abstracts a acidic proton. Okay, so now what will happen? So and we also know that in the organic chemistry, if you have taken a base in the reagent, then you have to check acidic proton in the molecule. Okay, then you have to check most acidic proton in the substrate. Okay, then you have to check the base, and you have to do abstraction of the most acidic proton. So first of all, you have the main task, the first task, you have to find which is a more acidic proton in this molecule, either this or either this. Okay, so let me explain you. Let me erase all this. Okay, yeah. So first of all, what happened? As you now seeing, this H is also here. This is also acidic proton, right? As you all know that this is also an acidic proton, and this is also an acidic proton, right? Right. So we have two acidic proton in this molecule. Now you have to decide the base. The base takes which proton? Either this proton or either this proton. You have to decide this. Okay. Okay, so you have to decide which is the more acidic proton. So either this one or either this one, CH3 proton. So now how can we decide? So let's see. Okay, so let me erase all this. Okay, so see here we have a cyclohexanone here, C double bond O, and here is a H here, and we have taken a reagent CH3 here. Okay, and here we have SME2, right? There is a SME2, SME, and here is a positive charge. Now we have taken, here is a base, right? Here is a base, H minus, right, and A plus. Okay, so what will happen now? Now see, this H and this H, these are the two acidic proton here, but you have to decide which one is the more acidic here, right? So what we have to do, so as you all know that after removal the proton, wait, after removal of the proton, right, of proton, you have to check the stability of the anion. Check the stability of anion, right? As you all know this, okay, you all know this thing, like how to compare the acidity of the proton, right? So I am not going into much details about that. Okay, so basically, so what happened? So if the base is taking this proton, then you will get something like this: CH2 here, and here is a negative charge, and here SME, and here is a positive charge. As you all know that that sulfur have a vacant orbital, so that's why this negative charge is a more stable here, more stable due to vacant d orbital conjugation, vacant d orbital conjugation, or you can say back bonding. Okay, so that's why this proton is a more acidic, most acidic proton. So what will we do now? So see here, now we have to do the reaction. Now we have find the most acidic proton. So this H is attached to this carbon is a more acidic, right? So that's why the base will take proton from this position. Okay, so let me erase all this. Okay, so see here we have something like this, cyclohexanone, and here is the H, and here we have CH3 here, and here we have SME2 plus here, right? So now what will happen? The base will come Na plus, and here is a H minus. So H minus will take proton, and you will find something like this, CH2. Here is an anion, and you will get SME2 plus. Okay, SME2 plus. Now what will happen? You have a substrate here, cyclohexanone here, right? And as you all know that this carbonyl is a electrophilic position. How it is electrophilic? So let me tell you. So here is a delta minus charge, and here is a delta positive charge. Will be polarized due to electronegativity difference between this carbon and this oxygen. So that's why this carbon is working as an electrophilic center. So that's why what happened now? See, this negative charge. Let me make a phrase here. This is our substrate here, right? So what happened now? This is our substrate. Okay, cyclohexanone, and this is working as an electrophile. Now we have a nucleophile here, CH2 minus, so it will attack on this carbonyl position and this electrophilic center, and now this pi bond will shift on the oxygen, and now you will get something like this. Something like this. Here is the O minus here, and here you will get CH2, and here SME2 plus. Now what happened? See, because sulfur has a positive charge here, right? Because sulfur has a positive charge here, as you all know this. Okay, this sulfur has a positive charge, so we want to make a neutralize, and how it will neutralize. So we have to make this leaving group, means we have to leave this group, and how it can leave. So basically simple, this O minus will attack at this carbon, and it will get leave, right? Here is a delta negative and here is a delta positive, because sulfur is a more electronegative, so that's why sulfur got a delta negative charge here, and the carbon is a less electronegative, that's why here is a delta positive charge. So that's why this O minus will attack on this carbon, and this SME2 will be leave as a neutral form. Okay, now you will get a product something like this, epoxide formation. This is our epoxide, and this is your final product of this reaction. Okay, this is your final product of this reaction. Let me underline this so you can see clearly. So this is our final product, epoxide formation, right? Final product, right? Okay, so this is a very simple case, right? Mostly people know this, right? But I have still told you all the steps, all the mechanisms in very much simplified way. Now I am taking example of a different variety of a Corey-Chaykovsky reaction. Okay, see. Now suppose I have something like this. pH, double bond here double bond, here pH, and I have taken here a reagent as a, I am taking here reagent something like this, Me2S, positive charge here, and here is a CH2 minus, right? And on this side I am taking SME2, positive charge here, but I have taken here cyanide also attached. This is our negative charge, right? So now what will happen? This question is very important. Okay, this question is very important and very conceptual. You have to understand, right? So now see here very clearly, very focused. Okay, pay attention on what I am saying. Okay, sorry. Yeah, see, so here is a also a negative charge, as you all know this, right? Here you have a negative charge also here, carbon, and here is also negative charge, but this negative charge is a stabilized. This negative charge is a stabilized, more stabilized, right? More stabilized due to CN, due to electron withdrawing group attached, due to EDZ group, electron EWZ, electron withdrawing group. This is our CN, this is our EWZ, so that's why this negative charge is more stabilized here in the comparison of this negative charge. Okay, so this is a less stable charge, this is a less stable negative charge, right? Or you can say this is unstabilized sulfur ylide, unstabilized sulfur ylide. Okay, YLID. I think you all know this, like Me2S here plus, and if you have something like this, then this molecule is called ylide, sulfur ylide, right? This is called sulfur ylide. Okay, so now what will happen? So let me erase all this. Okay, just wait. Okay, so yeah, let me erase all this. So here we have pH, double bond, here we have double bond here, right, and here is a pH. And I have taken here Me2S, here is a positive charge, and we have CH2 minus. Okay, so what happened? So see what happened. So this is our unstable. Okay, and on this side I have taken Me2S, positive charge here, and we have taken cyanide here attached, and here, and this is a negative charge. So this negative charge is a more stable here in the comparison of this negative charge, right? So suppose we got a product A here and we got a product here B. Now I am telling you the A is not equal to B. A is not equal to B. I will tell you why. Okay, I mean to say the A is not equal to B, the mechanism. Okay, the mechanism will be not same for A and B. Okay, the mechanism will not be same for this pathway and for this pathway. Okay, so there is a concept. I am telling you. Let's see. So this negative charge is only delocalized with this sulfur vacant orbital conjugation. Okay, so what happened? But this negative charge is a conjugation with this cyanide also and with this also, this sulfur also. So that's why we have to see here. So if we talk about this region, so this will simply attack on this carbonyl. Okay, right, this will just simply attack on this carbonyl, and this negative charge will go on here, and okay, so you will get something like this. Okay, so till now just think. Okay, so why this CH2 minus is attacking on this carbonyl? Okay, because this region is acting as a hard nucleophile, and this region is a soft nucleophile, right? Why it's soft? Because this negative charge is more delocalized with the cyanide ion, with the cyanide group, electron withdrawing group, and this sulfur also vacant d orbital conjugation. Okay, so that's why this negative charge is more dispersed, is more delocalized, and that's why this is a soft nucleophile. But in the case of this region, Me2SCH2 minus, here is this negative charge is only delocalized with the vacant orbital of a sulfur. Okay, so that's why it is a hard nucleophile in the comparison of this region. Okay, and as you all know that the hard nucleophile will attack on the hard electrophile, right? And the soft nucleophile will attack on the soft electrophile. As you all know this. Okay, hard will attack on hard, soft will attack on soft. This is the basic concept. I am assuming that you know this concept. Okay, these things are totally basics, totally juicy. Okay, so you have to know this whole thing. Okay, what is a hard nucleophile, what is a hard electrophile, what is a soft nucleophile, what is a soft electrophile. Okay, so the concept is hard nucleophile will attack on the hard nucleophile will attack on the hard electrophile, soft nucleophile will attack on the soft electrophile. Okay, so now let's see what happens. And one more important thing, as you all know this, between this carbonyl and this is our center, so this center is a hard electrophilic center, but this double bond is a soft center, right? This double bond is a soft center. Okay, I hope you all know this, how to decide hard and soft. Okay, I am assuming that you all know this basics, right? So this carbonyl C double bond is act as a hard electrophilic center, and this double bond is act as a soft center, right? So now what will happen, as I have already told you that hard nucleophile will attack on the hard nucleophile will attack on the hard electrophile, and the soft nucleophile will attack on the soft electrophile. Now see what will be the product of this A and B, right? So let's see. So first of all, we will see A product, right? So we have here pH, double bond, here is a double bond, here is a pH. Now I am taking here Me2 S positive here, right? And here is a CH2 minus here. So as we all know that this is acting as a hard nucleophile, so that's why, and this is our hard electrophile, hard electrophilic center, so that's why what happened, Me2S positive charge here is a CH2 minus, this negative charge will attack on this hard center, on this hard electrophilic center, and this bond will be gonna shift, and you will get something like this, PHO minus here, right, double bond here, pH here, and here CH2, and here SME2, right? And as you all know that between the carbon and the sulfur is a more electronegative. So here is a so here is a delta negative, and here is a delta positive, and that's why, because here sulfur got a positive charge, okay, so we have to make a stabilize, we have to make them leave, and how it will leave, this O minus will attack on this carbon, and it will leave as a SME2 as a neutral, and you will get a product, final product like this. Here is a pH, and here something like this. This is our final product of this reaction. Okay, this is our final product of this reaction. Now I am talking about the different region we have taken previous. Okay, let's see. I have taken here PHC double bond O here is a double bond, and we know here is a pH, and now I am taking a region here Me2S, here is a positive charge, but here I have attached the electron withdrawing group cyanide, okay, and now this region, now this sulfur halide is acting as a soft nucleophile. This region is acting as a soft nucleophile. Okay, why it's a soft nucleophile? Because this negative charge is a more conjugated, more delocalized, and that's why here is a this negative charge is more dispersed, is more delocalized. Okay, so that's why it will work as a soft nucleophile. And as you all know that the soft nucleophile will attack on the soft electrophilic center, and you also know that this double bond is working as a soft electrophilic center, okay. So now what happened, see, so that's why this negative charge will attack on the double bond, right, attack on the double bond here, this double bond goes on this one, and this pi bond will shift on the oxygen as a negative charge, and you will get something like this. Here is a O minus, and here is a double bond, and here is a pH, and here we have something like this. Just wait. So here, so here we have something like this, C triple bond N here, and here is a SME2 positive charge, right? And now what will happen? See, when the O minus charge will get a comeback, this double bond will attack on this center, on this carbon center, and this A semi will be leave, and now you will get a cyclopropane. Cyclopropane. Okay, you will get cyclopropane like a structure, something like this. Here, C triple bond N here, and this is our pH. Now you will get a cyclopropane type of structure. Okay, in the case of, if you take soft nucleophile, then this soft nucleophile will attack on the soft electrophilic center, and now you will get this product, final product, this one. Okay, so we can conclude that pH double bond here, pH, if you take unstabilized yield, unstabilized sulfur halide, then you will get a product like this. Okay, you will get like this product. And if you take a stabilized sulfur halide, then you will get a product something like this. This is your product from this pathway, and this is our product from this pathway. Now you got here cyclopropane type of structure, cyclopropane type compound product, and you will get here, in this case, epoxide. You will get epoxide. Okay, I hope you all understand the mechanism behind the average step. Okay, now one last question I am giving you. The question is very, very important. Suppose something like this, okay, suppose I have taken double bond over here, here is a double bond, and here is something like this. Okay, and now I am taking reagent. Here is a S double bond over here, and here is a Ame, and here is a Ame, and this is a CH2 minus. Okay, so now what will happen? So in this case, what will we do? You have two possibilities. Either you can attack on this position, either you can attack on this position, right? This is the A pathway, this is the B pathway. But how we can decide? But the main thing is how you decide which pathway is correct. This pathway, or this pathway. Which pathway is correct? So basically, you have to analyze this molecule. You have to analyze this region. What this region is saying. Okay. So basically, you see that here. You are seeing here this S double bond O group is attached to this CH2 minus, right? And this will work as a like a withdrawing group. Okay, like a withdrawing group, right? Withdrawing group. It means it will withdraw the electron density from this position, from this CH2 minus. Okay, yeah, of course it will be a positive charge here on the sulfur, right? So what will happen? Let me make this again. So here something like this, and here is a sulfur, and here is the Ame, and here we have CH2 minus here, and we have CH3, and of course there will be positive charge on the sulfur. Now this region is working as a soft nucleophile, right? And also it is a less reactive. Okay, because why it's less reactive? Because this negative charge due to this group S double bond O group is like acting as a withdrawing group, so it will withdraw the electron density from this carbon, from this CH2 minus. So that's why it will prefer to do attack on double bond. Okay, on double bond, right? Let me make this, and after that you will get a product something like this. Here is the O minus double bond, here Me, and here you have CH2 sulfur Me, here is the Me, and here is the positive charge. Now what happened? This O minus charge will get come back here, and now this double bond will attack on this carbon, and this whole sulfur group will be leave as a neutral form, and you will get something like this. This is our product. Okay, so you have to pay attention, like whenever C double bond O group is attached to the sulfur, then it will work as a soft nucleophile and it will attack at the soft center. Okay, right? Suppose if you take here Me, and here is a CH2 minus, right? So then of course it is a hard nucleophile, and that's why it will attack on this center, right? So that's all about this reaction, Corey-Chaykovsky reaction. I hope you all have understood very properly, and still if you have any doubt, you can ask me in the comment box. Okay, I will try to reply all of you, everyone. Okay, so that's all. Yeah, we will continue our this legacy of organic name reaction series. Okay, so, and if you have understand properly, clearly, then please like, share and subscribe our channel Chemistry Portal. Okay, on this platform we only talk about the organic chemistry, right? Okay, so तब तक के लिए टाटा, बाय बाय, see you soon in the next episode series of name reaction series. Okay, thank you for watching my video.